forest trees. So trees is, I know, you know, a normal tree, how it looks. You know, trees has root, branches. The branches only we'll be calling it as child and everything. So normally till now we saw about the linked list, then stack using linked list, queue using linked list, array and everything we saw it. Why do we want to suddenly jump into a tree? So tree will make us the searching or insertion a convenient way. See, normally, if I tell you, if I take an organization and I'm telling you these are the branches we have, and in that branches I have these many sections, and in these sections I have again division over there. Instead of telling like that, or giving a representation in a form of linked list in a longer way, anyway tree also we are going to make it use of linked list only. So instead of giving in a telling it as a whole, my representation will make it more clear. Maybe if I take a organization, if I give a chart model, and if I tell you go through this chart, it will be easy for me to understand. Like this, I'll be having some this, again some sub branches, then again here a child, then again some sub branches, here some child, here some child. So likewise means when I take this diagram, or when I look this representation itself, I'll tell that okay, this is the head, and this or this, after this there are more, no many divisions are there. So trees gives us a easy representation or easy understanding of the of any organization or any kind of applications. Also, if it is represented in form of a tree, it is very easy to for us to code, or for us to find out what is actually the content is, instead of writing it in a very large manner or representing it in some other way. Tree is an easy way of understanding. It is a hierarchical structure where it gives the easiness of understanding about each and every nodes and its connectivity. So these are the entire topics which we are going to see. Representation. So you should know what is a tree, what is a binary tree. Both have a difference. And no, tree and binary tree even okay, but the binary tree and binary search tree is have a little bit of difference. Okay, and expression. These are how the calculations. Then types of trees will be threaded, will be there, AVL, B tree. There is B trees and red black trees, and splay trees is also there. So these are the kind of trees which you are going to learn one by one. So in this AVL, binary search tree is a very important topic, and AVL is also a very important one, which most of the, when you get in 16 marks question, you will be getting definitely from BST and AVL, anyone. Likewise you'll be getting, and for that the other trees are not important, I'm not telling you. Very important thing is mostly, and if you know about BST, all others will be depending on this BST only, binary search tree. So normally, see, linear access for linked list will be it will be too high. So the solution only, even that linked list, see, when I am giving a connectivity like this to, then I am drawing like this, then I am taking another one to this. So likewise, if I have a hierarchical structure, if I keep on representing like this till the end, it will be very difficult for the particular even the algorithm to search from here to here, here to here, here to here, here, like this. Instead, this linked list itself you will be representing as trees. Here, this. Again, here you will be having one more child, one more. Linked list, that is the tree itself, will be represented in form of linked list. It will have a left and a right pointer. So it is easy to access the particular elements if for a large institution or a company or any other, if it is arranged in form of a tree. So that solution only, we are grouping the data into trees. Okay, and but another one, in linked list and the other whatever stack and queue, everything will be linear data structures. That is, it will be in order. In stack even you can see that you will be having in order. In queue also, some adding up in the last you will be having in order. But tree is not like no order will be there in trees. It has a left child, right side, something will be there. There is nothing, no orders will be followed. The data will not be in linear way. Okay, so it is a non-linear. Even graph also is a tree, and graph only is a non-linear data structure. And it's the hierarchical relationship that is more important. And the worst case, and this I'll tell you when I take that. So if I tell you now, it won't understand what about O of n and this. And normally searching will be O of n, because each element has to be searched. And other things, when we learn, I'll tell you the complexity. So now tree consists of collection of nodes, hierarchical node. So this will not be a tree, because see here why it is not a tree. Can anyone answer? This is not a tree. Why?
It's true.
D and E are connected.
What
There's a
one?
cycle. There's a
Yeah,
cycle.
there is a cycle. Okay. So there is a cycle, there is a loop. Otherwise, I can tell you. So here it cannot be a tree. It can be that this is a tree, this is a tree. Okay. And these are the terminology which we are going to see: root, edge, parent, child, sibling, degree, internal node, leaf node, level, height, depth, and subtree. So we will see one by one. What is a root? The starting node. So if a tree is in such a way, this will be called, this is called as a root node, and these all will be called as your child node, and this is called as your leaf node. Without child will be your leaf node. Leaf node means there are no child for it. It will be without child. That is leaf node. And what is called as edge then? Edge will be, that is your connectivity. Okay, so A to B and C. B is having two childs, D and E. D is having F, one child. So in general, I can tell you, if there are n nodes, then you will be having n minus 1 edges. So a tree with n nodes will have n minus 1 edges. So 1, 2, 3, 4, 5, 6 nodes are there. See my edges: 1, that is, this is my edge, this is my edge, 1, 2, 3, 4, 5 edge only. So there are 5 edges only. So all tree with n nodes will have 5 edges. Similarly, parent node, I think you will be knowing. If a children node are branches connecting to other nodes, that is, this is called as root node. But anyway, B and C's parent is A only. Similarly, the D and E parent will be B. B is a parent but no child, nothing is, so it's not a B cannot, it is like a leaf node. So F is having a parent of. So in this diagram, I can tell you B and D will be parents. Okay, and so that's what represent here. Child also, you can either tell it as node that is descendant of any node is a child. Child node will be, so this will be called as ancestor. This will be called as descendant. That is child nodes. So C is a child, E, D, F, B, everything is a child. But compared to B, B is also child of A, but not to this parent. So siblings, what can be the siblings? Nodes with the same parents are called siblings. Let us see here, I think you know it. B and C are siblings. D and E are siblings. Okay, because it has a common parent. D and E's parent is B, and B and C's parent is A. And what is now called as degree? This degree, all you should know it very well, because there is in 5th unit, there is a topic called topological sorting, where you sort based upon the degree alone. So degree of a node will be how many number of children for that particular node. For A, the degree is, see here, it is having only two child. So the degree of A is 2. For B, it is having 3 childs are there. So B's degree is 3. But for C, it is 0. For D, it is 0. E and F, it is 0. Okay. But when I ask you to, maybe if I'm asking you node wise, you can tell its corresponding how many children it is having. That is the degree of the particular node. But when I ask you about the degree of the tree, what is the degree of this particular tree? Entire, in general, I'm asking, what is the degree of this particular tree? Means what you have to answer, what the answer should be, which node is having the highest child or highest degree, I can tell you, or large number of children. That will be having your the node of the tree. That is the degree of the tree. For example, A is having only 2, but B is having 3. So in this, the total number of child which B node is having is 3. So I will tell that my entire degree of the entire tree is 3. For example, if my C is having 4 nodes, so like 4 childs, like this I'm having 4. So my C's degree will be 4 and my degree of the tree also will be 4 only. Clear? Clear, students, of this degree now?
Yes, ma'am.
Yeah.
Yes, ma'am. Yes.
Yes. So highest degree will be the high and larger the node having the larger number of child or children, whatever it is. Okay. So there is this, if it is 4, it will be 4. Otherwise, that's possible. Similarly, what is called as internal nodes and what is called as that is internal node only called as non-terminal nodes. These both are same. Non-terminal nodes and internal node is same. So nodes with minimum one child. Okay, even this B is an internal node. C is an that is, this is an internal. No, this will not be. I think here it is different. This will be, that is, terminal nodes, or you can tell it as, yeah, okay, non-terminal internal and terminal will be called as leaf, correct? So here this is called as your leaf node, or you can tell it as terminal nodes, that's all. But B, E, B, D, these all will be your internal nodes. This is your leaf node, which is called as terminal nodes, and B and D will be your non-terminal nodes. Okay, so here you can see here, or you can also call it as external nodes also, terminal nodes, external nodes, and leaf nodes. Okay, so here that's correct. Here this should be external actually. Okay, because it does not have a child, so it is considered as a leaf node. So leaf node will be also called as external or terminal. This
And then what
will
about
be
B,
your
ma'am?
internal.
Shouldn't it be also
B,
external node?
B will be, wait. B is an internal node. B will be internal node, non-terminal nodes.
Ma'am, D for
Non-terminal.
dog.
What, ma? Yeah,
D.
D.
B. D will be
I'm
your
asking
leaf.
about D, ma'am.
D is your external node.
Okay.
Or you can tell it as terminal node, or you can tell it as leaf node. Okay. So external, or that is here clearly it is given with no child. Okay, no child is leaf node, that is called as your external node, or that you can call it as terminal nodes also. The C is also the same. Okay, so now here tree terminal. So this is what your about your external and internal nodes. Now about the level of the tree. As you give it an index, so normally an array index will be giving it as 0, 1 and 2. So here also your level will be starting with 0. So 0th level, first level, second level, third level. So these levels are, the levels will be like this. Root node will be 0, next child levels all. Okay, now what is the height? So calculation of height is also very important. Height and depth. See very carefully. Height will be from the number of edges in the longest path from the node to the leaf. That means from your from, if I'm asking a height of the particular node, you have to calculate the edges, number of edges from the particular node to the leaf node. Okay, particular node to the leaf, this is the line which you have to keep it in mind, particular node to the leaf. So so for A, see, from A to leaf I can tell you 1, 2, 3, there are 3 edges, right? A to B is one edge, B to D is one edge, D to G is one edge. So there are 3 edges. So my height of A is 3. When I take B to leaf, there are 2 edges. So height of B is 2. When I take D to 1, there is D to leaf, there is only one edge. So height of D is 1. But when I take maybe E, F or C, all are considered as your leaf node, and even G also. These all are leaf nodes. So leaf nodes, height of any leaf node will be 0, because from your height itself is from the particular node to the leaf. So when I take the height of a leaf node, there is no more edges or down. So leaf node will be always 0. And what will be the height of the tree is the height of the root node, because root node will be having the largest height. So if a particular height of a particular node is being asked, then you can count from the particular node till the leaf node. But if a height of a tree is being asked, take the highest one. That is your highest one, where it will be the height of the root node only will be having the highest one. So if you are having a tree like this, again, like this, again, maybe I'm drawing like this. Okay, what is the height of this tree now? What is the height of this tree?
6.
6. Yes. Okay, correct. Because you have to take from here 1, 2, 3, 4. So if you come here there is one more to the longest one only here. So 4, 5, 6. Because this is the longest edges from the particular node to the particular leaf node. So 6. Okay. So this is how which you have to proceed for the particular height of the tree and height of the node. So in this case, you can see that height of the leaf node will be 0, but when you come to the depth of the root node will be 0. Depth of the leaf node will be high, because how we are taking the depth is edges from root node to the particular node, edges. So depth root node to the particular node for the A it is 0. Okay, root node to the particular node. So otherwise from the node to the root, I can tell you that is the correct one. If you are taking the depth, means you have to take it from the particular that is from this particular node to the, not to the leaf. When you go to the leaf, it becomes the height. You go backwards from the node to the root. From the node to the root only will be your depth. So for A, there is no way, so it is 0. So depth of the tree will be the longest path from the root to the leaf. That is, leaf only will be having the highest depth, because I told you when you take a depth, you have to go from the node to the root, node to root. For the height, it will be node to the leaf. Okay, so node to the root is, see here, for B it is only 1. So C also it is only 1. For D it is 1 and 2. For E also 1, 2. For F also it is 1, 2. But for G it is 1, this side 1, 2, 3. Okay. So from the node to the root will be your depth. From the node to the leaf will be your height. That is, this comes like this. 1, 2, 3. So here the arrow mark will go upwards. Okay, so understood this now. So what is the depth of this tree now? Depth of this tree will be 6, same. Okay, so depth of the tree you have to take from this. So if they ask you a particular node, by depth of this node, what is the depth? 1. So not 0, 1 ma, it is from here to here. You have one edge in between. 1. 0 will be for A, root node alone, it will be 0, because there is no prolong from that particular node, path
So,
from
ma'am,
that one.
height of tree is always equal to depth of tree.
Yeah, yes, height of the tree will be equal to the depth of the tree, because maybe if there are any number of leaves down, from the leaf to here it will be same, and from there to down also it will be same only. Okay, it is equal only. Okay, so next, but the node will differ. Okay, each node will differ, only the tree will be equal, height of the
For tree only.
yeah, tree is same. Now subtree, I think you know, each child of a tree forms a subtree. Maybe A is having this, I can take this, that there is a circle over here, see the blue circle. This is fully my left child of A, and this is fully my right child of A. When I take B, again D and this will be the left, this will be the right. When I take D, only G will be my left. So this is very important, subtree forming, because for traversal we are going to follow this procedure only. So when the problem comes, I'll tell you. This is not needed actually, disjoint trees, I don't want to confuse now. Now this path will be like when you want to take from A to G. What is the path from A to G? For the, since there is no direction you can take here, it will be a down arrow only. It won't be anything. So you can like A to B, B to D, D to G. So the path number is 3 actually. But when they ask you a path, you have to tell it as in case of this, like this: A to B, B to D, D to G. For A to G, the path will be A, B, D, G. For A to E, the path will be A, B, E. Similarly, for A to F, the path will be A, B, F. Okay, so that's what given here also, defined as a sequence of nodes when you go from here to here. But when I ask you what is the length of the particular path, you have to give the count. A to B it is 1, B to D it is 1, D to G it is 1. So 3. So number of edges will be the path. So when I ask you the path from A to E, what you will tell? What is the length of the path from A to E? Length of
2.
the 2, because A to B is 1, B to E is 1, another 1. So 1 plus 1, 2. So in this case it is 3. This is the path. Now coming to the ancestor and descendant. Ancestor, what all the parents or the grandparents will be the ancestors, and child, its child, or that all will be the descendant. So A to B means A will be your ancestor of B, B will be the descendant of, that is the child of B. So in this case, A path of, that is okay. A is ancestor for, A will be the ancestor for B, then C, then D, then G, everything. And G will be the, A is the ancestor of all. And G will be the descendant of all, because it is the last child in the particular tree. Okay, so this is what ancestor and the descendant. Now when I come to binary tree, a binary tree means it is the topmost element is called the root node. All one or more, it can have any number. Binary tree has no restrictions. It can have a tree, and binary tree will be mostly similar, but each node has 1 or 2 or at most. Binary tree means at most 2 childs, but it can have either 1 child or no child also, not a problem, or maximum 2 childs it will be having, at most 2 kids for binary tree. But it is not restricted. A tree will be having many number of kids, but binary will be having only 0, 1 or 2, that's all in binary. But binary search, binary, and there is another one term called as complete binary tree and full binary tree. I'll tell you that difference. So here a tree can have any number of child, but a binary tree will be having a 0. It can be child, there is no child, or 1, or to the maximum only 2 kids. Okay, that is only called as binary. So binary main thing is allowed 0, 1, 0, 1 and 2. So there are 4 types of binary tree: full binary tree, complete, skewed and extended. So in this, what is called as full binary tree? Full binary tree means it is, full binary tree will be called as strictly, that is completely, it will have only 2 children. Every node in the tree will have 2 children, or else all the no child means all will be in the same level. All will have equal number of nodes. A is having B, and B, that is 2 children, A, B and C. B is having D and E, C is having F and G. Again, if you want to proceed, you can give like D is having again 2, E is having any 2. If you are not putting for F and G, then this won't become a full binary tree. Make it be clear. Your binary tree can have 0 or 1 or 2. Binary, full binary tree will be, all will be having either 2 children. Maybe if I draw like this, D is having 2 children, E is having 2 children, but I'm not giving for F and G, then this is not a full binary tree. When it can be a full binary tree is F, then your G. Okay, when it comes, it can be a full binary tree for all 2 children. Okay, so that is what called as your, it can have 0. Why we are telling it as 0 is your leaf node has no children, right? All are in the same level, so it can be 0, but strictly it should be two children. Now when I come, when I erase this I told you when F and G are not having children, this is not a full binary tree. Instead, I can tell you it is a complete binary tree. Okay, so here one more thing is it should be all your leaf nodes should be in the same level. That is only called as your what is that full binary tree. So I think full binary tree, one more example, anywhere else it is given. No, complete, not complete. Okay, this is okay, complete. So in complete binary tree there is one difference. Your the last level, that is, see here in this level you can see this tree is, it is also having two children only, but we don't have what is that, here G is not having, and here see here one child is not there, and here there are two childs not there. So this is called as complete binary tree. Full binary tree will have again here one more node and here two nodes. That will be full binary tree. But in complete binary tree it can be like this. It should have two children, or else any one it can have. Either this also is allowed, but if it all are in the same level, then it will be a full binary tree. All the nodes need to be, except the last level, all the nodes need to be completely filled. So this is complete. This is not complete because you can see here not complete, and here also it is not here you can tell it as A, B, C, D, E, and this is also not a complete binary tree. So this is a complete binary tree. So this is not a complete binary tree. This is not, I think this example has one error. I'll change it. This one you can take it as an example. And another one I want to tell you, for all the levels, it will be correct exactly as four nodes. Not exactly four nodes. Maybe this is 0th level, one node. If this level is level 1, so it will be 2 power 1. So 2 nodes. So this is level 2. So 2 power 2. So 4 nodes. 1, 2, 3, 4. So this is 0th level. Level 0, level 1, level 2, and this is level 3. Okay, so 2 power 1, it will have the 2 power, 2 power n, how many 2 power the particular level. So 2 power n, 2 power 2, this will be 2 power 3. So here what happens is 2 power 3, 1, 2, 3, 4, 5. So in this case, it is not filled. If it is filled equally, then that will be your full binary tree. Okay, if it is completely equal, that will be a full binary tree. So now skewed binary tree will be this level. You can see one end it will be, this is left skewed, this is right skewed. So if your nodes are in one particular way skewed, that is it is having a left, no right child, it is having a left and skewed, left skewed tree, this is right skewed tree. So this is called as your skewed trees. Extended binary tree will be, each node will have either 2 child or 0 child. So that is, see here, this is binary tree only, because you can see here it is having 2, or it is binary tree. I told you either it can have 1 child also in binary tree. Not, I'm not telling about a full or complete, just a binary tree. So binary tree 2 child, here it is 2 child, here it is only 1 child, and here it is having 2 child. But what is called as extended binary tree is all having, filling up the remaining part also. You can see here one more child is added, one more child is added. For this I'm adding to extended. So you can add if you want it, but these all are, we are not going to use it. So this is called as your extended binary tree. If you add more childs to it, it becomes a, this is a normal binary tree. When you add 2 more childs to become 2 equal child for each of the particular node, that becomes your extended binary mode, binary child. So now this is the most important thing which you want to see, representation of binary tree. So normal linked list, you know, you will have a data and your next pointer, right? So when you go for the next pointer, that is it will hold the address of the next ones. Now that is your normal linked list. In your doubly linked list, you have a previous pointer and your next pointer. So here your node is divided into three portions: data, left child pointer, and right child pointer. So A is your parent node, and B is having the left child is B and right child is C. So B's address, A will be holding the address of B here, and in right child pointer, it will hold the address of C. Clear? Students, are you clear?
Yes, ma'am.
Yes.
Yes, ma'am.
So when the x is null, to represent null only it is given as x, because C has no left child. C has no left child, so it is called as null. Okay. So null is only
Hello.
represented. This is null. X is null. So left child is null, but it has a right child F over it. Similarly, for B, there is a left child and a right child. That is, D is there and E is there. So you should not put a null over here. If the particular node is not having left or right child, you can make it as null. So for D also you have a left and right, so pointing to left and right, but G is a leaf node which does not have a left and right child, so null null. H also does not have a left and null, and E also does not have, F also does not have. So your linked list representation will be your node. You have two pointers, that's all, as you give it in previous and next. You have here as left and right child, and this is the value which you want to insert, or the data. So now see in this diagram, this is just values which are given in the index. For example, see here, initially all are that is the node, and there is no, it is for null here it is represented as -1. So there is no left and right child. That is the initial representation. Maybe I can tell you as a head node. Now when you come it as a first node, you see A is the first node. Its left is stored in the value 5. So go and see in the 5, you will have the B in 5. B is in 5. So left child is position is 5. It's just an example. And the C where it is, C is in 8. That's what the right child, it is represented as 8. Okay. Similarly, when I go for the next one, B, you go and see in the B. So you look where D is in 10. So B's left will be holding the 10 address, and where E is in 12. So this is some sort of address, just we have given for representation, that's all. So B is stored in 12. So here this is actually 5, the address is 5, and C is 8. That's the meaning. Okay. And for B, D is in 10, that is in this position, and B's right side is holding E right. So that is, this will be 12. And C is having, now again your C is not having left child, so it is -1. And C's right is F right. So F, where F is in 4. So C will be having here 4. This is what will be stored over here. Okay, this is the